All right, let's talk about one of the coolest puzzles in all of science. It took the brightest minds nearly a century to solve it. How do you take the complete chaos of all the chemical elements and turn it into the beautiful, elegant order of the periodic table? It's a fantastic story, full of false starts, amazing insights, and even one legendary dream.
So let's start with a really basic question. Why do scientists have this obsession with classifying and organizing everything? Well, honestly, it's for the same reason you organize anything in your life, to make sense of the world and to be able to find what you're looking for.
Seriously, just picture this. You walk into a grocery store and there are no aisles. Ketchup is next to motor oil, which is piled on top of the bananas. It's total chaos, right? Well, that's exactly what chemistry felt like for a long time. You had all these elements, but no system, no way to understand how they related to each other. It was pretty clear that to get anywhere, somebody had to start building some aisles.
And so, the quest for order began. Scientists started hunting for patterns, for any faint clues they could find that hinted at some kind of hidden logic behind all the elemental mess.
You know, the very first attempt was super simple, almost too simple. They were like, okay, some of this stuff is shiny and conducts electricity. Let's call those metals. The other stuff, we'll call it nonmetals. Easy peasy. But then, these weird elements called metalloids showed up. They were kind of in-betweeners with properties of both. And just like that simple little system just broke.
So, a new player steps onto the scene, a German chemist named Johann Dobereiner. And this guy, he had a thing for the number 3. Instead of a simple two-way split, he started noticing a really cool mathematical pattern. He found that some elements just seemed to naturally hang out in families of 3.
He came up with this idea he called the law of triads, and it was actually pretty slick. So you take a little family of 3 elements, like lithium, sodium, and potassium. Dobereiner figured out that if you take the atomic mass of the lightest one and the heaviest one and find the average, boom, you get the mass of the guy right in the middle. And this wasn't just a math trick. The middle element's properties were also a perfect blend of the other two.
Now, this was a fantastic clue, a really brilliant insight. But it wasn't the whole story. The triad thing only worked for a handful of element families, and when new elements were discovered, it just couldn't keep up. So, a great first step for sure, but the puzzle was a long, long way from being solved.
All right, next up we have John Newlands. He was an English scientist, and get this, he was a huge music lover. And he started thinking, hey, if music has repeating patterns, maybe chemistry does too?
And that's how he came up with his law of octaves. You know how in music the 8th note is basically the same as the first one, just a bit higher? Newlands thought the elements did the same thing. If you line them up by their atomic mass, every 8th element has similar properties. For example, lithium is here, and 8 spots later, sodium, its chemical twin.
Okay, let's give Newlands his due. He gave us a huge concept, periodicity. That's the idea that properties repeat at regular intervals. That was pure genius. The problem was, his system itself wasn't quite right. It worked great up until you got to calcium, and then the whole musical analogy just fell flat. His table had no room for new discoveries, and he was even cramming multiple elements into the same slot just to make his rule work. So, a game-changing idea, but definitely not the final answer.
And that, my friends, brings us to the absolute legend of this story, Dmitri Mendeleev. This is the guy who took all these early clues and made a leap that would completely change the game forever.
Here it is, Mendeleev's big idea, his periodic law. He proposed that if you arrange the elements by their atomic masses, their properties will repeat in a predictable, periodic way. This simple statement became the very bedrock of his entire table.
Now there's this awesome story about how he had his big breakthrough. Apparently, he'd been wrestling with this puzzle for ages, writing each element and its properties on a little card, almost like a game of solitaire. He was completely exhausted, fell asleep at his desk, and, in a dream, he saw all the cards just arrange themselves perfectly into a grid. He woke up and immediately scribbled it all down. Now, who knows if that's exactly how it happened, but it perfectly captures that lightning-in-a-bottle moment of genius.
But this is where Mendeleev went from being smart to being an absolute visionary. See, when he was arranging his cards, if an element didn't fit the pattern, he didn't try to force it. Instead, he did something incredibly bold. He left a blank space. He basically said, there's an element that goes here, we just haven't found it yet. He even predicted what these missing elements would be like. He called one icosilicon, meaning below silicon, and described its mass, its density, everything. And then, years later, scientists discovered germanium. And guess what? Its properties were a near-perfect match. I mean, can you imagine? That predictive power was just mind-blowing. It was the ultimate proof that he was on the right track. So, Mendeleev's table was a total game changer. But it wasn't perfect. There were these little glitches, a few unsolved puzzles, and cracks in his masterpiece that just kept nagging at him.
So what were the problems? Well, for one, there was hydrogen. Where does it go? It kind of acts like it belongs in group 1, but it also has properties like the elements in group 7. It was a chemical loner. Then you had these anomalous pairs. To make elements like cobalt and nickel fit in the right families based on their properties, he actually had to break his own rule and put them out of order by mass. And maybe the biggest mystery of all, he could see the pattern, the periodicity, but he had no clue why it happened. What was the underlying cause?
But honestly, the biggest problem, the one that could have torn his whole beautiful system apart, came down to one little thing: isotopes. So isotopes are just different versions of the same element that have slightly different masses. Think carbon-12 and carbon-14. Now, if your whole table is organized by mass, well then those two should get their own separate spots, right? But they're both carbon. This was a major contradiction, and his table had no answer for it.
So who's going to solve this mess? The answer came from a brilliant young physicist named Henry Moseley. He's the guy who found the final, crucial key to unlock the whole thing. What Moseley discovered was truly revolutionary. He found that the true fundamental identity of an element isn't its weight, it's its atomic number, which is just the number of protons in its core. It is a unique fingerprint. Every single carbon atom in the universe has 6 protons. Every oxygen atom has 8. That's it. It was like everyone had been organizing a library by the color of the book covers, and Moseley walked in and said, guys, shouldn't we be using the author's last name?
And just like that, by switching the organizing principle from atomic mass to atomic number, everything clicked into place. The whole isotope problem? Gone. See, carbon-12 and carbon-14 have different masses, sure, but they both have 6 protons, so they share one spot, because they are the same element. It was just so elegant.
So with Moseley's incredible discovery, all the pieces of the puzzle were finally on the table. It was time to build the definitive, modern version that we all know and use today. The final design came from another giant, the physicist Niels Bohr. He took Moseley's law and structured the table into the 18 columns or groups and 7 rows that we see today. And here's the beautiful final reveal. An element's atomic number doesn't just identify it, it also determines how its electrons are arranged. And elements in the same column have similar electron setups, which is why they have similar chemical properties. The big why that had stumped Mendeleev was finally answered.
And there you have it. After almost 100 years of false starts, brilliant ideas, and incredible discoveries, the periodic table was finally complete. It's this beautiful testament to how science works, building on each other's work over time. But you know, even this masterpiece has one little nagging mystery left. That old problem with hydrogen. Where does it really belong? Is it in group 1, group 7, or is it just its own weird thing entirely? It's just a great little reminder that in science, the search for answers, for that perfect understanding, it's never really over.